Hello everyone, my name is Mike Cross and we are going to be discussing a whole lot of chemistry. So in order to start this out, we need to talk about measurements. What are they? Why are they useful? Anytime you think of science, you probably think of measurements, but there are a couple of important things that you might not have really thought about when it comes to measurements. The first is, well, pretty obvious that measurements are quantitative observations. They have to have a number, right? You can't just have a measurement without some kind of numerical attachment. And then the second thing is that there has to be a unit, an agreed upon standard that everyone recognizes. So for instance, we might talk about someone being 6 feet tall or something weighing 2.7 kilograms, because kilograms and feet are agreed upon standards that everyone recognizes. What that means for us is that every single measurement has to have a number and a unit. You cannot just give a number without actually having some unit attached to it. So for instance, let's say that you're driving down the road and you happen to get pulled over, and you might be going a little fast, and the officer says, do you know how fast you were going? And you say, well, yes, I do. And he says, well, if you look back there at the sign, it says that the speed limit is 45. And you could say, well, it turns out though that I looked at the sign there and there's no unit attached, so I thought that the 45 was meters per second, not miles per hour. You should have put a unit on there. And so they'll just back away and say, you know what, you're right. I didn't realize that you were such a wise person. You try it and let me know how it works. All right, so what's the next thing that we need to worry about when it comes to measurements? Well, there are a couple of tools that we're going to use to help us in our measurements. The first is scientific notation, and the second is going to be significant figures, or sig figs. All right, so for scientific notation, let's talk about this in a little more detail. This is a nice tool that allows us to write very large and very small numbers. So for instance, if I asked you to write the sun's diameter, that's a pretty big number, right? If we write it in meters. And 1,400,000,000,000 meters approximately. Now, one of the problems with this is that if you try to enter that into your calculator, many calculators only have an 8-digit maximum, so you wouldn't even be able to enter that into your calculator. So we need a better way of writing these things. This also works with very small numbers, 0.00000003, because again, it's difficult to type that into your calculator, and also you can make errors when you're trying to count how many zeros and so forth. And so scientific notation comes to the rescue here. So what we're going to do is we're going to write this number, but we're going to write it as a single digit, a decimal point, and then the rest of the numbers there, especially significant figures when we talk about those in a little bit. And then the second part of this is that we have this over here, times 10 to the something. It's raised to a power, and that power actually tells us how many times we've moved the decimal place. So let's actually practice this, and I'll hopefully explain it a little more clearly. So let's try writing a couple of these numbers in scientific notation. So let's go ahead and practice these. The way that we would do this is, the first thing is you would make sure that you have a single digit, right? The 1 in this case, followed by a decimal point, and then followed by the rest of the numbers. So in this case, a 2, a 3, and a 4. Now, the next step is you're always going to write times 10 to the something. So in this case, you'll notice that the decimal point is here, but we're going to actually move it 2 places to the left in order to kind of wedge it in between the 1 and the 2 there. So we moved it 2 places, so we're going to put a 2 here. So 1.234 times 10 to the second. All right, let's go ahead and try this again. So in this case, we have 8, and then the decimal point's already there, which is really nice. We need to include the rest of the numbers, and then times 10 to the something, right, this exponent. Now, how many times did we move the decimal in this case? Well, we actually didn't move it at all. and so we moved it 0 places, so we should actually write 0. So in this case, this is kind of a silly one to write. There's no reason to write 8.012 times 10 to the 0 when you could just write 8.012. So scientific notation is not always necessary, but we should at least understand how to use it. For this next one, again, we're going to put a single digit, in this case a 1, and then the decimal point, followed by a 4 and a 5. We're going to go ahead and leave off those zeros there. Now, you'll notice that in this case, we don't actually see a decimal written. So it's implied that it's at the end of the number. And we're going to move that 1, 2, 3, 4, 5 spaces. 5 spaces in order to wedge it between the 1 and the 4. And you might say, well, why put it there? Well, because that's the rule. You need a single digit, and then a decimal point, and then the rest of your numbers. So in this case, we're going to write times 10. And how many places do we move it? We moved it 5, right? 1, 2, 3, 4, 5. So that's going to be a 10 to the 5, 10 to the 5th. All right. Over here, notice that we have a whole bunch of zeros at the beginning of the number. We're going to leave those off, and we're going to start with a 2. And then we're going to put our decimal point, and then we have a 3 and a 4 after that. Now we need to figure out how many times to move the decimal point in order to wedge it between the 2 and the 3 here. So here's the decimal point. We're going to move it 1, 2, 3 places. So we're going to write times 10 to the 3rd. Now if I just left it like this, it would be confusing because 2.34 times 10 to the 3rd means that I'd move the decimal point 3 places to the left, kind of like we did in these other examples over here. But instead we moved it 3 places to the right, which means that I'm actually going to put a negative sign there to imply that I moved it 3 places to the right. Now, some people memorize, the rule that if you move the decimal to the left, you should have a positive exponent, and if you move it to the right, you should have a negative exponent, and that's perfectly valid, and that works very well. However, I usually think of it in these terms. I try to remember that if I have a really large number, right, a number that's larger than 1, so in these two examples here, I'm going to actually have a positive exponent. I always think of positive as being big, larger and so forth. So a really big number greater than 1 is going to have a positive exponent. A number like this is going to have a negative exponent because it's smaller than 1. It's a really tiny number. I think of negative as being tiny. That's just how I remember it. But whatever works for you is the way that you should remember it. Okay, so clear the screen to have a little more space so it's not so confusing. Let's go ahead and look at a few more of these. So in this case we have a 2, and then we put our decimal point here, and then we need the rest of the digits. So a 5, and then a 2, and a 5. It's going to be times 10 to the, let's see, we moved the decimal point only 1 place in order to wedge it between that first 2 and the 5. So 10 to the 1st. All right. Should it be positive or negative? It should be positive because the number is bigger than 1, or in other words, we move the decimal 1 place to the left. Let's try another one of these. Let's see. Here we have a 1, a 2, and a 3. We need the decimal point right in between the first and the second digit. Perfect. And now we write 10 to the, let's see, we move the decimal point 2 places, so it's going to be a 2, and you're right, it should be negative because we moved it to the right, or in other words, the number is smaller than 1. Let's go ahead and try another one. This is another one of those that is kind of silly because we don't even need to move the decimal. So 1.45 times 10 to the 0. So usually I wouldn't bother writing something like that, but it's a good trick question on an exam or something. All right, let's look at this one. We have an 8, and then our decimal, and then a 7, 0, 6 times 10 to the, let's see, here we're going to move it 1, 2, 3, 4, 5, 6 places. Positive or negative? Should be negative, because we have a very small number. We move the decimal point to the right. Now when you're working with scientific notation, many times you're going to be entering this into your calculator. And I want you to be able to understand this so that you don't mess up on a problem simply because you didn't have the calculator kung fu necessary to be able to work with this. So let's try typing in a number. You should probably pull out your calculator that you're planning on using for this course, and let's say that you are entering 5.4 times 10 to the negative 6th. Now there are a couple of ways to do this. First way is pretty simple. You would just type in 5.4 and then we can go ahead and write or type in times 10, and then you can use the little caret symbol here on your calculator, and that means raise it to a certain exponent. The next thing you need to do is enter the negative sign. So calculators can have this different ways. Some calculators will actually have a negative symbol in parentheses. Others will have a little, plus minus sign. So whatever your calculator has, you can go ahead and enter that here. What you don't want to do is you don't want to enter in the subtraction sign, because that will give you an error. So make sure you do the negative symbol and then 6th. So that's how you type it on many calculators. Now there are some calculators that will actually have a nice shortcut symbol. So in those cases you can write or type 5.4, and then there's a little EE button. So some calculators will have an EE, some will have a little button that says times 10 to the x or something like that. But in that case, what that actually refers to is it's saying that you're typing in times 10 to the whatever. So just like that. Now, after that, all you need to do is type in the negative 6 and you're done. Okay, so hopefully your calculator functions in one of those various ways. If not, shoot me an email. I can help you figure it out. The next tool that we can use when we're doing measurements are significant figures. I'll always refer to these as sig figs just because it's easier. So when you hear me talk about sig figs, then you'll know that I mean significant figures. Some textbooks will call these significant digits. It's all the same thing. Now, why are these important? Well, they're important because they allow us to show precision when we're writing our numbers. They allow us to tell how precise a measurement is and not to underestimate or over-exaggerate the precision that we have. So for instance, if I were to measure something with a ruler, I might measure it as 2.50 centimeters. And that tells how precise my measurement is. I couldn't report it as 2.500000 centimeters, because that would imply that I have a much more precise measuring tool than I actually have. Now, a couple of things to remember. That first, these sig figs only apply to measured numbers. That's very important. It doesn't apply to counted numbers. So for instance, I know that I have 5 fingers on each hand and 5 toes on each foot. Those are counted numbers. I know that it's not 5.01 fingers or 4.98 fingers on each hand. Also, anytime you have a definition or a conversion factor, so for instance, 1 meter is exactly 100 centimeters, or 1 foot is exactly 12 inches, not 12.1 inches and not 11.3 inches. This is exact numbers, so we don't need to worry about significant figures in those cases. Or if you prefer to think of it in this way, you can say that measured numbers counted numbers or definitions have infinite sig figs. Now, there are some rules for these. You don't really need to understand why these are the rules. You just need to make sure that you follow these rules. So, in this example here, 183.23 grams, you can see that the numbers in green are the certain numbers. We know for sure that our, whatever we're weighing is 183.2 something grams. But the number in red is the estimated digit. So that number might be off a little bit. It's kind of like when you step on your bathroom scale and that last digit kind of fluctuates a little bit. You always wait until it goes down and then you jump off the scale, right? Because then you can justify all those extra bacon cheeseburgers you've been eating. So the same thing applies whenever we have any kind of measurement. So how do we actually report our measurements? Well, let me actually go go ahead and try drawing something here. You'll see that I'm definitely not an art major because I have absolutely no skills. But let's say that you were using a thermometer, right? Something like this. And a thermometer will have little tick marks, or what we call graduations, that tell us, the actual, the units on it. So for instance, maybe this thermometer is not very accurate, and it is, only accurate to every 1 degree Fahrenheit. So these are degrees Fahrenheit here. And let's say that you walk into a lab and you're measuring something, and you notice that the little alcohol inside of there is, up to about that level. So now, if I asked you to measure this, you would kind of look at the top of that, and you'd say, oh, well, I know that's definitely somewhere between, it's definitely more than 4, and definitely less than 5. So that 4 there is certain. Everyone agrees on that. No one would say, oh yeah, that's probably about 7.2. No, it's 4 point something. But when I look at this, I might estimate that final digit and say, oh, that's probably about 4.6 degrees Fahrenheit. My lab partner might walk in and say, oh no, you know what, I think that's actually about 4.5 degrees Fahrenheit. And someone else might say, no, I think that's probably more like 4.7 degrees Fahrenheit. So you can see in that final digit, in that final significant figure, that there's some uncertainty, and we might not all agree on it. So it's important that we put the appropriate number of sig figs so that we know where that uncertainty lies, because the uncertainty will always lie in your last significant figure. Now, one other thing that you should note is when you are working in the lab with graduated cylinders, which looks something along these lines here. Okay, this is for measuring volume, and it'll have little graduations along it. And when you fill this up with a liquid, you'll actually see that it forms what's called a meniscus. So a meniscus is the little dip in the liquid. And it's very important to remember that these graduated cylinders are calibrated so that you look at the bottom of the meniscus. So if this were, 1, 2, 3, 4, 5, and 6, I might say that that is approximately, 4.7 milliliters. Also remember, because it's a measurement, we have to have a quantitative observation or a number. We also need to make sure that we have a unit. So let's go over the rules for determining sig figs, and then we'll actually practice on a couple of them. So the first rule is non-zero digits always significant. If it's not a 0, it has to be significant. So here in this number we have 3 sig figs, just abbreviate it SF. Here on this next one, 1, 2, 3, 4 sig figs. Simple, right? If it's not a 0, it's automatically significant. The second rule, applies to zeros, right? So zeros are going to be significant if they're sandwiched between 2 other non-zero digits. So for instance here, back up for a second. Here we go. Okay, so the 2 is automatically significant, as is the 7 and the 5. And then these 2 zeros in between are also significant. These are interior zeros. I call them sandwich zeros because I like sandwiches. So that gives us a total of 5 sig figs here. All right, on this next one, doesn't even matter that there's a decimal point in there. We have a 4 and a 7 that are significant, and then the 2 zeros in the middle are also significant. So 4 sig figs. The next one has an important note at the end of it. Zeros are significant at the end of a number if that number contains a decimal point. Okay, that's important because you'll notice on the other one, if it doesn't contain a decimal point, it's not significant. Now, it does not matter where that decimal point is in the number. Okay, it can be at the beginning, at the end, but trailing zeros or zeros at the end of the number become significant if there's a decimal point. So here, the 5 and the 1, automatically significant. Here are 3 trailing zeros. There's a decimal point in the number, therefore they are all significant. So we have a grand total of 5 sig figs there. Here we have a 9, a 5, a 3, and a 7, all significant. The 0 as well is significant because it's a trailing 0, or 0 at the end of a number, and there is a decimal point. So it looks like 5 again. Okay, here the 8 is significant because it's not a 0, and then here's a trailing 0. Notice there is a decimal point there, so it has to be significant as well. So 2 sig figs. All right, what about times when zeros are not significant? Okay, they are not significant if they are at the beginning of a number. So in this case we only have 1 sig fig because we have a whole bunch of leading zeros at the beginning of a number, and it doesn't matter whether or not there's a decimal point in there. Now, one thing to remember is that when you have, when I say significant, that doesn't mean important or not important, right? So significant just means that affects our precision. Okay, these zeros at the beginning of a number are still important because they're placeholders, and they tell us that this is 0.5 grams and not 5 grams or 50 grams or 0.005 grams, right? So those zeros are important, but they are not significant. They do not count towards our number of sig figs. Now the next time that zeros are not significant is if they're at the end of a number, if they're a trailing 0, and if that number does not contain a decimal point. Okay, so this is the opposite of the rule on the last slide. So in this case we have a 3 and a 7, automatically significant. There's a trailing 0 there, but there's no decimal point, so not significant. 2 sig figs there. Okay, and then this one only has 1 sig fig. Again, I'm not saying that these zeros at the end are not important. They are. They're placeholders, but they are not significant zeros. Okay. So actually, let me show you a quick thing that might help, maybe, or at least, to explain this, or maybe it might just be fun. So, I always think of interior zeros or sandwich zeros, kind of the cream filling in an Oreo, right? I love Oreos. When I was a kid, we used to get like a whole package of them. I'd sit there and I'd scrape out, you pull them apart, and then you lick out the cream filling. Or in my case, what I'd do is I'd take it and I'd actually sit there and I'd stack it up, so you'd get a little more cream filling, and a little more, and a little more, and a little more, and a little more, right? And this is just like sandwich zeros. It doesn't matter whether you have 1 or 2 or 3 or 4 or 5 or 10 sandwich zeros in there. They're all significant zeros, okay? Thank you. So now that we understand the rules for determining the number of sig figs, let's go ahead and actually try applying these rules and practicing to count sig figs in some numbers that we're given. So in this first example, we know that the 5 and the 3 are significant because they're not zeros, so we already know we have 2. What about this 0 there in the middle? Is that one significant? Well, yes, it is, because it's a sandwich 0, right? It's between two other non-zero digits. We also have a 0 at the end of a number. Now, remember that this is kind of that if-then statement. So this 0 is significant because there's a decimal point somewhere in the number. So in this case, we actually have 4 sig figs for our number. Okay, let's try this next one. Here we have the 3 and a 2, guaranteed to be significant, right? Because they're not zeros. We also have a couple of zeros at the beginning of the number. Zeros at the beginning are never, ever, ever significant, so only 2 sig figs. Okay, in this next one, we have a 7. We have a couple of zeros at the end of a number. Remember, that's the if-then thing. These zeros are not significant because there's not a decimal place written, right? The decimal is implied at the end. If I were to put a decimal point, an actual written decimal point, anywhere in that number, all of those trailing zeros would automatically become significant. Now, some books will actually tell you that these zeros are ambiguous. Because they're ambiguous, I always refer to them as not being significant. Let's try this one. We have some trailing zeros this time, but there is a decimal point in the number, so all of those trailing zeros are now significant. So a grand total of 5 sig figs here. Okay, looking up at here, we have a 2 and a 5 that are significant. We have a couple of sandwich zeros in there, and we have a couple of zeros that are at the beginning of the number. Those zeros at the beginning are never significant. So 4 sig figs in our case. Okay, here we have a couple of non-zero digits, and then what about those zeros at the end? Significant, right? Because there's a decimal point in the number. So all 5 of those digits are significant. All right, in this case, we have a trailing 0, a 0 at the end. There is a decimal point in the number, therefore it's significant. We have a bunch of zeros at the beginning of the number. Those are not significant. Ooh, and then I threw in one here with scientific notation. So how do you count sig figs when you're doing scientific notation? Well, it turns out that you have to make sure that you only count sig figs in the original number here. Okay, we do not need to worry about those. That 10 to the negative fourth here when we're counting sig figs. So in this case, the 5 is significant. What about the 0? Yep, it's significant as well because there's a decimal point somewhere in the number. So 2 sig figs. Now, one thing that I do want you to note is that when we are writing a number in scientific notation, or we're going back into regular notation from scientific notation, it's important that we make sure that we maintain the same number of sig figs in each case. So I'm going to go ahead and move this up here, and let's go ahead and write that in regular notation. So in this case, it's a 0.00050. So I'm actually going to write it that way. Notice that I've moved, if I go back into scientific notation, I would have to move the decimal point 1, 2, 3, 4 if I want to wedge it right there between the 5 and the 0. So it's 10 to the negative fourth, and it's negative because this is a very small number, right? It's less than 1, or you can think of it that I had to move the decimal place to the right in order to to move the decimal over into there. Now the other thing that you should note about this is that remember that we had 2 sig figs here in our number in scientific notation. We have 2 sig figs here in regular notation. The 5 significant, and also that trailing 0 is significant because of the decimal point in the number. Now, sometimes I'll simply ask you to count the number of sig figs in a number, but oftentimes you'll actually be expected to perform a calculation, sometimes multiple calculations, and then apply the sig fig rules to your final answer. So how do you do that? Well, the first thing is that there are different rules whether you're doing multiplication, division, or addition, subtraction. So if a problem involves division and or multiplication, then you need to make sure that you follow this rule. What we're going to do is count the number of sig figs in each of our original numbers, and then we are going to go with the lowest number of sig figs. I always think of this as like going with the weakest link. So for instance, if I asked you to do 5.0 times 3.00, that's obviously 15, right? And notice that I have 2 sig figs here, and I have 1, 2, 3 sig figs here. So 2 sig figs and 3 sig figs. My quote-unquote worst number only has 2 sig figs, so my final answer should have 2 sig figs. So in this case, I would just write 15. I wouldn't write 15.0 or 15.00. Now the next rule applies to addition and or subtraction. So if you are doing addition and or subtraction, you have to make sure that you follow the rule that says to count your decimal places, not your sig figs. Count the number of decimal places in each of your original numbers, and then round your answer to the lowest number of decimal places. So multiplication and division, count your sig figs. In the case of addition subtraction, count your decimal places. So if the number was 4.5 plus 1.03, I can go ahead and add that up, and it's 5.533, but I need to go ahead and count my sig figs, right? Or not my sig figs, count my decimal places. Here we have 1 decimal place, here we have 3 decimal places, which means that I need to cut my answer off right there. So my final answer should be reported as 5.5. So your calculator would spit out this, but I would expect you, to answer 5.5. Now, what about rounding? Well, you already know the rules for rounding, right? You've been doing this your whole life. But just as a reminder, if the first digit to be dropped is 0 to 4, you're going to round down. If it's 5 to 9, you round up. So for instance, if it was 1.362 and I asked you to round that to 2 sig figs, you would say, okay, I need to cut it off there. So do I round this up to 4 or down to 3? Well, this digit here is a 6, so I'm going to round up to 1.4. If it was 0.0031 and I asked you to round that to 1 sig fig, you'd say, well, these zeros over here are not significant, right? They're important placeholders, but they're not significant. So here's my first sig fig. So I need to chop it off right there. So I would write this as 0.003, and I would round down to 3, not up to 0.004, because this digit here is a 1. So let's go ahead and discuss some of the experimental quantities that might be useful when we are talking about chemistry. Okay, so the experimental quantities that you should know about would be first mass, right? This is the amount of stuff in an object, the amount of matter that is in an object. This is typically measured in kilograms or grams, right? This is a little bit different than weight, even though we sometimes use the two terms interchangeably, and I'll even catch myself doing that. But mass is how much stuff is in me. Weight is the actual force of gravity on the stuff that's in me, right? So it's actually gravity pulling me down onto like a scale, whereas mass is how much stuff is actually, inside of me. So weight will change depending on where you're at. So for instance, you go up high into the mountains at high elevation, there's slightly less gravity because you're further away from the core of the earth, and so you'll actually weigh slightly less. Okay? If you go to the moon, my weight on the moon is only 1/6 what my weight is here on Earth. Okay, it's a great weight loss plan, right? So I've lost 5/6 of my weight, but the amount of stuff, I'd still have a mass of about 74 kilograms, whether I'm here on Earth or whether I'm on the moon, because the amount of stuff in me hasn't changed. Now the next thing would be length. This is obviously just the distance between 2 points, right? You can measure that in meters or centimeters. And then also volume. Volume is how much space something takes up. Okay, it's the amount of, if you have a cube, you could measure the volume of that cube and figure out how much space is occupied by it. We typically measure this in liters. Here in the U.S. we measure a lot of things in gallons, milk and so forth, but it's kind of weird because we measure our soda in liters. We buy it in liter or 2-liter bottles. We measure our gasoline in gallons though. So why is it that soda's special and we buy our milk in gallon jugs? So but in the rest of the world they use liters, and in science we'll always use liters because it's part of the metric system. Now one thing I do want you to know is that 1 milliliter, and we'll talk about what milli means in a little bit, is the exact same thing as a cubic centimeter, which can be written as cm cubed, or cc, cubic centimeter. So 1 milliliter is exactly 1 cubic centimeter, or 1 cc. So when you're watching one of those medical shows and they're like, I need 2 cc's of epinephrine, stat, you can turn to that specialist, someone and say, actually those are milliliters, that's about a thimbleful of epinephrine. And then they just throw popcorn at you and they stop watching videos with you. And then also time, measured in seconds. So you know what this is. You're probably counting down the seconds before this video is over. Alright, so if you grew up outside of the U.S., you're probably very familiar with the metric system because it's an extremely useful and powerful system of measurements. And it makes so much more sense than the system that we unfortunately use in the United States. But this is the system that we're going to use throughout this course and in all of science. So you definitely want to familiarize yourself with it. Now, one of the important things about the metric system is that there are prefixes that are going to be attached to things. So like if you're using the old British system, we might say, okay, there's 12 inches in 1 foot, or 5,280 feet in 1 mile. Or anyone know how many teaspoons are in a tablespoon? I think it's 3. I can never remember. And then I think there's 4 tablespoons in a quarter cup. And then I don't even know how many pints are in a gallon, and all these kind of crazy numbers. So the metric system is very nice, because if I say, well, how many millimeters are in a centimeter? 10. How many centimeters in a decimeter? 10. How many decimeters in a meter? 10. How many meters in a kilometer? 1,000, right? They're all based on factors of 10. So that's the really nice thing about this. So there are a whole bunch of different units. These are not all common. I mean, not many things in chemistry are measured in mega, which means a million. Sometimes we'll measure things in kilo, like kilograms or kilometers. Decimeters, not super common, but you'll see a lot of like centimeters and centigrams, millimeters and milligrams, extremely popular. If you go into something like biotechnology, then you'll deal with a lot of microliter quantities, or even nanogram quantities of DNA and so forth. So even though there are a whole bunch of different conversion factors out there that would allow us to say that there are a million microliters in a liter and so forth, the 3 that I definitely expect you to know, because we use these so many times, would be these. 1 gram equals 100 centigrams. This is easy to remember because there's 100 cents in a dollar, right? 100 years is a century, so centi means 100, right? Also, 1 gram is 1,000 milligrams. I think this is pretty easy to remember as well, because milli means 1,000, right? A millennium is 1,000 years. So, I think that one's pretty easy to remember. And then also 1,000 grams is 1 kilogram. Now, another thing to note is, whenever I say this, that these are the only 3 that you definitely need to know. I'm even going to put a little star by them because they're that important. People always complain and say, oh, well, you said we only need to know these 3, but then you asked me, how many centiliters are in a liter. And that's totally different. And, well, no, it's not, because 100 centiliters is a liter, just like 100 centigrams is a gram. And 1 meter is 100 centimeters, right? So notice that it's the prefixes and how they relate to the base unit. So if I say 1 liter is how many milliliters, you'd say, oh, milli means 1,000, right? So it's 1,000 milliliters. Or if I say 1,000 meters is how many kilometers, right? Oh, it's 1, because 1,000 grams is a kilogram, 1,000 meters is a kilometer. So the prefixes are what's important. The base units you can mix and match. I could say 1,000, when we talk about energy, we talk about calories. 1,000 calories is equal to 1 kilocalorie, right? So even though this is kind of a weird unit, it doesn't matter, because the kilo is what's important, right? So 1,000 calories is 1 kilocalorie. Now, in order to do any kind of conversion problem, where we're converting liters into milliliters or so forth, we're going to use a technique known as dimensional analysis. Some people would call this the factor label method. I actually refer to this as dominoes, because I like to play this little game with my kids with dominoes, and it teaches them dimensional analysis. It's great, right? Growing up with a chemistry geek as your dad. So here's how the game works. You have a whole bunch of dominoes, right? So let's say, and when they were young, we used to use these little picture dominoes. So let's say that you had a domino, and it has a triangle on one side and a squiggly line on the other side. And then this one has a triangle on it, and then it has a, let's say a circle on it. And then this one has a triangle, this one has a circle, let's erase that real quick. Okay, this one has a circle and a squiggle on it. Okay, so these are the dominoes that you have. Now, the way this game works is that you put a line down the center, and then you go ahead and, let's say that I start with a triangle on the top of this line, and let's say that I happen to have a squiggle mark on the bottom of this line. Well, my job, if I'm going to play this game, is to go ahead and put one or more dominoes here in the center in order to cancel them out, right? So if there's a triangle on top, I need to make sure that I put a triangle on the bottom. If there's a squiggle mark on the bottom, I have to have a squiggle mark on the top, right? And as soon as all of those pictures cancel, then it's game over and I've won. There's much rejoicing in the land. Everybody's happy. So which domino am I going to use? Well, I'm going to use this one right here because notice that it has a triangle and a squiggle. Now I could write it as is, right, with a triangle and a squiggle, but that wouldn't cancel things out, okay? Because oh yeah, I need that triangle to be on the bottom, right? So luckily, dominoes are easy to kind of rotate around however you want. So I'm going to go ahead and just rotate that. I'm going to put the triangle portion on the bottom and the squiggle on the top. So now notice that if I go to cancel these things, the triangle cancels top and bottom. The squiggle mark cancels top and bottom, and there's much rejoicing and everyone's happy, right? Okay, so that's pretty simple. Now obviously it gets a little trickier than this, right? So my kids are always losing things. So let's say that they actually lost, let's say that they lost this domino, right? So it's gone. Can't find it anywhere. So could I still complete this problem using the remaining dominoes? Well, yeah, I could. It's going to take 2 dominoes this time, not just 1. But I can still do it, right? So, for instance, let's see. In this case, I'm going to go ahead and use this one first. Do I want the triangle on the top or the bottom? Well, I want it on the bottom, correct? Because that way it'll cancel out. Now, this is a domino, so I can't just break it in half and use only the triangle half. If I use this top half here, I also have to use this other half as well. So that means that on the other half of this domino, I have a circle. Now, at this point, am I done with the problem? Well, no. I mean, the triangle's canceled, so that's good, but I still have more to go. So, because the circle and the squiggle don't cancel each other out. So I'm going to go ahead and use this other domino that I have. Do I want the circle on the top or the bottom? I want it on the bottom, right? And then the squiggle has to go on the top. Now by doing this, notice that the circle cancels top and bottom, squiggle mark cancels top and bottom. And again, much rejoicing in the land. Yay, and spiky hair. Okay, so in this case, I completed the problem, but it took me a little longer. It took me, 2 steps, which is totally fine. You can have 1, 2, 3, 5, 10, 100, dominoes or conversion factors there in the center of your problem, and it doesn't make any difference. It'll still be totally fine. Now, if that seems silly and childish, it kind of is, right? But it turns out that this is the exact same procedure that you're going to be working with anytime you work an actual problem. So let's see what an actual problem might look like. It might say something like this. 3.5 meters is equivalent to how many centimeters? Okay, so that's the problem. Pretty simple, and many of you can just do this in your head, but I'm going to go ahead and work through it just so that we can understand what's going on. So, this is how I always set up my problem. Okay, just like before, I have a line down the middle, and then I like to have a box in the top left-hand side and a box in the bottom right-hand side with a little equal sign right there before that bottom box. The number that's given in the problem is always going to go here in the top right-hand corner. So 3.5, and it's very vitally important that we always include the unit. Also notice it's important I use the right unit. So in this case, 3.5 meters. Now the next thing is I'm always going to make sure that I put my question mark and its corresponding unit in the bottom right-hand corner. So this is the basic setup for it. Now what I need here in the middle is 1 or more dominoes, or in other words, conversion factors that I can use in order to to make this work. Now, if you remember, hopefully you remember from like 2 minutes ago, when I talked about 1 meter is equal to 100 centimeters, right? Centi means 100th, so 100 cents is $1, 100 centimeters is a meter. Let's see. Now, in this case, what I'm focusing on is I'm focusing on these units. That's just like those symbols that we were using either, but instead of circles and triangles and squiggle marks and so forth, now I'm actually using, units, but it's the exact same procedure. I just have to make sure that whenever I drag the unit somewhere, I drag the number with it. So in this case, I have 1/2 of my domino here, and you can draw it as a domino with this line where the equal sign is. So now it looks like a domino. Do I want my meter on the top or the bottom? Well, if I write it on the top and then write 100 centimeters here, when I go to cancel things, meters do not cancel out centimeters on the bottom, so that doesn't work. But that's okay, it's easy to erase this. So I want my 1 meter on the bottom, which means that my 100 centimeters has to go up on top. So now I go ahead and check to make sure that my units cancel. Meters cancels meters. I'm not canceling out numbers, I'm just canceling out the units, the symbols, right, the pictures. So in this case, centimeters cancels out centimeters. So there's much rejoicing in the land. Actually, half rejoicing, because this is only half the problem. It's actually the tough half, though, so that's good. So now that I've canceled out the units, I know that I'm done with the problem. All I need to do now is just what I call plug and chug. Just taking all these numbers, plugging them into my calculator, and I'm done. So in every case, what I'm going to do is I'm going to take all of the numbers on the top and multiply them together. So in this case, 3.5 times 100 is 350. And then I'm going to take all the numbers on the bottom. In this case, there's only one number, right? It's a 1. But there could be 3 or 4 or 5 numbers on the bottom. And it doesn't matter. You just take all of those numbers, multiply them together. So in this case, it's 1. So 350 on the top, 1 on the bottom. Using my amazing mental math abilities, that comes out to 350. Now, the only other thing I need to do is I need to figure out what is my unit over here. Well, my question mark was centimeters, right? So that means that my final unit should be centimeters. Whatever my question mark is, that's what this is. So what I'm saying is that 3.5 meters is the exact same thing as saying 350 centimeters. And again, if you can do this in your head, more power to you, you should do it. But there are going to be some problems, especially when we get to stoichiometry, where it's not quite so easy to work a problem like this in your head. You might have 3 or 4 dominoes there in the center. It takes a little more work, so it's important that we understand this now. So let's go ahead and let's practice a little bit more to make sure that we understand how to work these problems, because honestly, this is probably the most important skill you're going to learn from this entire course is dimensional analysis or unit conversions or whatever you want to call it. This is like the skill you need to know, whether you're going into nursing and you're calculating dosages, whether you're planning to work in a high-tech lab and you need to calculate making a certain concentration of a solution, or whether you're working in biotechnology. It doesn't matter. You're going to be using this a lot, and you're going to be using it throughout this entire course. So you're going to get so tired of me talking about dominoes that you're going to want to pull out your hair, but this is important. So please make sure that you understand what's going on here. All right, so let's try another one of these. Let's make this one just a little bit more difficult. Let's say that you have 0.403 let's say centiliters, and I want to know how many milliliters is that equal to. Okay, simple enough problem, right? Let's go ahead and set this up. Put a square in the top right, or the top left, and then a square in the bottom right. Now, what goes in my top left-hand box? You're right, it's always the number that's given along with its corresponding unit. So in this case, 0.403 centiliters. And then my question mark always goes in the bottom right. So question mark milliliters. Now, do we have a conversion factor or a domino that goes straight from centiliters to milliliters? Well, there is one, and if you remember it, great. But it's not one of those that I told you should memorize. So can we do this with more than one domino? Yeah, we definitely can. So we know that 1 meter is, we're talking about liters this time, right? So 1 liter is 100 centiliters. I also know that 1 liter is 1,000 milliliters, right? So I can go ahead and work through this problem using two separate dominoes, just like I did using those symbols a little earlier. So I'm going to go ahead and use this one first. Now, where do I want my centiliters? Do I want that top or bottom? Well, I want that on the bottom because that's, that'll cancel out the centiliters that I already have on top. So I'm going to write 100 centiliters on the bottom, which means that the 1 liter has to go on top. All right, that's good. The next step would be to use this one over here. Now, this case, I have a liter up on top, right? So I'm going to go ahead and put 1 liter on the bottom and put 1,000 milliliters on the top. Now, I can go ahead and check to make sure I've set up this problem correctly. And this is the thing I like most about dimensional analysis, is that you can check yourself before you wreck yourself, right? So in this case, I just check and see centiliters, top and bottom, that's good. Liters, top and bottom, that's good. Milliliters, top and bottom, that's good. And so that way I know exactly, how to start. I know that I always start with the number given in the problem. I know where I finish, because that's where my question mark is. And then I can also check to make sure that everything cancels, and if it does, then I know I've set up the problem correctly. And as long as I don't, mess up on my actual entering this into the calculator, I'll be perfectly fine. So let's see, what's my next step? Oh, I just need to multiply all my top numbers together, then multiply all the bottom numbers together, and then divide, right? So 0.403 times 1 times 1,000 is equal to 403, right? And then on the bottom we have 100 times 1, and that is equal to, 100. And then just divide top over bottom. So 403 divided by 100 comes out to be 4.03. And what are my units? Well, my question mark was milliliters, so my unit has to be milliliters. So 0.403 centiliters is the exact same thing as 4.03 milliliters. Now the next thing I wanted to mention here is, what about the sig figs, right? Well, in this case, we are doing a multiplication division problem, right? Notice all the multiplication symbols, and then we did division over here. So anytime you do a dimensional analysis problem, it's a multiplication/division problem, which, if you remember, we need to count sig figs and then go with the lowest number of sig figs, right? So here we have a 4, a 3, and a sandwich 0. This 0 at the beginning is not significant because it's a placeholder 0. It's at the beginning of the number. So we only have 3 sig figs to start with. What about the rest of our numbers? Well, notice that all of these are conversion factors, right? Those are definitions. 1 liter is by definition 100 centiliters. 1 liter is by definition 1,000 milliliters. So you can think of those as having infinite sig figs. So the only number that we really need to worry about is our first number, which had 3 sig figs. So that means that our final answer has to have 3 sig figs as well. So 1, 2, 3. Perfect. So this is exactly how we should report our final answer, 4.03 milliliters. Let's go ahead and try one more of these and make sure that we understand completely how this works, because again, this is vitally important. So this time it might say something along the lines of, let's say you have 925,000 millimeters, and I want to know how many kilometers is that equal to. Well, just like before, we're going to go ahead and put a box in our top left-hand corner, a box in our bottom right-hand corner, and then what goes in the top left? It's the number. Okay, so 925,000, and make sure that we include the units with that, millimeters, and then our question mark kilometers has to pop up in the bottom right-hand box. All right. Now, what about our dominoes in the middle? Is there a conversion that goes straight from millimeters to kilometers? Yes, there is, and if you remember it, great. But I'm just going to go ahead and always convert back to the base unit. I think that's easy, and it makes it easy for me. So I know that 1 meter is the same thing as 1,000 millimeters. I also know that 1 kilometer is equal to 1,000 meters. All right, so I'm going to go ahead and use this one first. I'm going to put that here. I'm going to put, let's put millimeters on the bottom, right? Why did we do that? Well, because remember we have millimeters here, so we need millimeters here. Top and bottom so they cancel. The other half of this domino has to say meters because that's what this half of the domino says up here. So that looks so far so good, right? What about this? Now we have this meters on the top, which means we need meters on the bottom. So we need this on the bottom. So we have to write 1,000 meters on the bottom, which means 1 kilometer has to go up on top. Let's go ahead and double check that we set this up properly. Millimeters cancels millimeters, meters cancels meters, kilometers cancels kilometers, and everything cancels. If something didn't cancel, it's not the end of the world. It just means that we messed up somewhere along the way. We flipped one of our dominoes. Maybe in this case, maybe we put kilometers on the bottom instead of the top, in which case meters would not cancel kilometers, and we'd know we messed up. All we'd have to do is erase a little bit and flip our domino, and then it should work out just fine. Now at this point, the next step we need to do is go ahead and multiply. So I'm going to multiply 925,000 times 1 times 1, which is 925,000. And then 1,000 times 1,000, which is, I'm actually going to be sneaky and write this in scientific notation just to throw you off a little bit. 1 times 10 to the 6th, okay, or in other words, 1 million. Now, I need to go ahead and punch that into my calculator. Now, you could type in 925,000 divided by 1 times 10 to the 6th into your calculator. One thing I would note is that anytime I have scientific notation in my calculator when I'm doing a calculation, I like to put parentheses around it, just because of order of operations, and sometimes the calculator will misinterpret what you mean. So, good idea to punch that in like that. 925,000 over 1 times 10 to the 6th, which comes out to 0.925. Now, what about units? Well, question mark kilometers, so this answer has to be in kilometers. How about sig figs? Well, let's look at our original number. We had 1, 2, 3. Are these significant zeros? No, because they're at the end of a number and there's no decimal point in the number. So 3 sig figs, so our quote-unquote worst number only has 3 sig figs, so our answer can only have 3 sig figs. What about this 0? That's not significant, right? It's at the beginning of a number, not significant. So 3 sig figs, so I would report my answer just like this, 0.925 kilometers. Now, I understand that this can be a little bit, tiresome and so forth, and I hope I didn't really, drill this into your brain too horribly bad and bore you to tears, but it really is important. So let's go ahead and illustrate this with a quick little magic trick and see if it helps out. All right, so let's go ahead and take a card. Okay, we'll take the top card, which happens to be the Jack of Spades. We'll set it down. Right now, normally I'd have an assistant come in and actually, poke their finger in, but let's say that they choose this card, which happens to be a 10 of hearts. We can go ahead and put that back into the deck, and with the snap of the fingers, we can actually change the card that was on the table into a 10 of hearts, right? Now, this is, pause that for a second, this is exactly like what we're doing with a, with a conversion problem, is that I can take something that's measured in milliliters and quickly and easily with the snap of my fingers and a few buttons on the calculator convert that to a different unit, and it's totally fine. So let's continue on, see if we can do this again. So we're going to go ahead and make 3 separate stacks with these cards. I'm going to go ahead and pick up that 10 of hearts. And remember that it's right there on top. We can choose any deck we want, plop it on top, and with the snap of the fingers we can go ahead and actually change that top card into a 10 of hearts. In fact, we can actually move it over to the other one because we're so good at conversions, right? We can convert these things all over the place. So there's our 10 of hearts. Now, pause this for a second. It turns out that you probably already know exactly how this trick works, right? Because since we're so good at converting things, you might notice that we can actually convert the entire deck into a 10 of hearts, right? Which makes this trick really easy. Now, the real trick, though, is not to have something like a 10 of hearts, but instead to actually change it into like a 9 of clubs, right? So with a little shake, snap of the fingers, we can actually convert all of these back into regular cards, right? And that's exactly how a conversion problem works, okay? Being able to convert from one to another. So we're almost done here. Hopefully you enjoyed that brief little interlude of randomness. But what we need to talk about now is something known as density, right? So density is not like George McFly in Back to the Future where it's like, you are my density. But anyway, density is a formula of mass over volume, right? So it's a ratio of how much stuff is in an object divided by how much space that object takes up, right? You can think of it as how much matter is, how tightly packed something is. So something like air has a very, very low density. Okay? There's a lot of empty space in it. Whereas something like lead has a very high density because there's a lot of stuff packed into a very compact area. Now, we can write this as D for density equals mass over volume. We'll use this formula quite a bit. But density is what's termed an intensive property, which means that it doesn't matter how much of the sample or how big your sample is, the density will always be the same. So what I mean is, if you have a few drops of water and you calculate the density, the mass per unit volume of that water, it'll come out to about 1.0 grams per milliliter. Right? If you go and take an entire swimming pool full of water and you measure the density, it'll still come out to about 1.0 grams per milliliter because it's an intensive property. Whereas mass and volume are both extensive properties. So those change depending on how much you have, right? If I have a small block of silver, it's going to have, a small mass. If I have a large block of silver, it's going to have a large mass. And the same thing with volume. So those are extensive properties, whereas density is an intensive property, which means that density can actually be used to identify what a sample is. So this actually goes back to a story about a Greek philosopher by the name of Archimedes that you might have heard of. So the story goes, and who knows if it's actually true, but it's funny. So that's all that matters. So Archimedes was one day called before the king, and the king says, "Archimedes, I have just had this crown made of pure gold, but I'm kind of suspicious that the goldsmith is actually kind of watering down the gold, that he actually removed some of the gold, mixed in some copper or silver or whatever, and then kept some of the gold for himself. And so I want you, Archimedes, to figure out whether or not this crown is made of pure gold." So Archimedes knew that he could actually use the density of the crown to figure out whether it's gold or not. He could compare that to the density of a block of pure gold that he knew was pure. And if they match, then it's pure gold. And if not, then that's some trouble. So, but here's the problem, right? He knew that he could easily get the mass of the crown, so he sticks it on a little scale and he measures it and he figures out the mass of the crown. That part's easy. But how do you figure out the volume, right? This is kind of the question here. How do you calculate the volume of something? Now, he could have taken the crown and pounded it into like a cube and then done length times width times height, and that's how you calculate the volume of a cube. But the king would probably execute him for messing up his crown, so he needed another method to figure out the volume. And so he did like most of us do when we need to think. He went and he took a bath. And the story goes that as he climbs into the bath, he noticed that the water level rises. You've seen this before. My kids already know this because they always fill up the bathtub to like the very, very tip top of it, and then they climb in, the water sloshes over the edge, and then I get mad at them, and they're like, "Oh, it's just Archimedes' principle, Dad." I'm like, "Oh, you little science kids, it's okay." So what happened, or the kind of the inspiration that Archimedes had was that, wait, the volume of water that he displaced was the volume of his body. And so he was so excited by this that the story goes that he jumps out of the bath and goes running down the street completely naked, shouting, "Eureka," which is Greek for "I have found it, and I have no pants on." And suddenly, he runs back to his lab, hopefully puts, some pants on, and then he carefully takes a container and, with little markings on it, and then he fills that container full of water, and he marks the level of the water, right? So we do this in the lab today, called water displacement. He marks the volume of this water, and then he goes ahead and he puts in, this crown. Oh, that's a lovely looking crown right there. Okay, he puts in the crown, and obviously what's going to happen is the water level rises. Okay, so the water level goes up here, and suddenly he has this new volume. He can measure this new volume, and then he realizes that the difference in between that, the difference in volume, is the volume of the crown. He now has the mass, he now has the volume, he plugs those in, crunches the numbers, and suddenly he figures out the density. The story goes that the crown was not pure gold. Archimedes goes and he tells the king, and the goldsmith is executed, and everyone lives happily ever after, except for the goldsmith. So the rule is, never mess with the king, right? You want to make sure that you know exactly what you're doing when you are working with density. So the next thing that we can do with density is we can actually use density as a conversion factor. So a problem might say something like this, since we've been talking about Archimedes. I could tell you that gold has a density of 19.3 grams per cubic centimeter, right? This is the density. How much does 7.2 cubic centimeters of gold weigh? So this is the mass. Now there are two ways that we could work this problem. We know that the formula is D equals m over v. We already know the density, and we already know the mass, so we could go ahead and plug those in and then solve for the missing volume, and that would be perfectly fine, and you'd get the right answer. But that involves algebra, and some people are like, oh, algebra, I don't want to touch it, right? So I personally love algebra, but if you don't like doing it that way, you can also set it up just like the domino problems that we've been doing earlier, if you think that's easier. And this will give you the exact same answers. So let me go ahead and clear this up a little bit, just so that we don't worry so much about that. And let's go ahead and try working this problem using dimensional analysis. So the first thing that I need to do is I need to look at these numbers that are given in the problem. I'm given this number, I'm given this number. So usually I'm only given one number, but in this case I'm given two. Now the important thing to note is that this is written as grams per cubic centimeter. So I can actually rewrite that as 19.3 grams is equal to 1 cubic centimeter. Okay? Now that's perfectly legal to do, because remember that if it's 19.3 grams per cubic centimeter, if I had 1 cubic centimeter, it would equal a mass of 19.3 grams. So why did I go through all the hassle of writing it this way? Well, the reason is because now this is a domino. It's a conversion factor, right? And so I know that that number has to go here in the middle. I can never start, over here in the top left-hand box with this domino. That doesn't work. So the only other number given in the problem is 7.2 cubic centimeters. Okay, and that means, what's my question mark? Well, in this case it doesn't really explicitly say it, but it says how much does it weigh? So we want to know grams, right? We want to know the mass of this thing. So now I have this domino that's going to go here in the center of my problem. Now do I want the grams on the top, or do I want the cubic centimeters on the top? Or which one do I want on the bottom? Well, notice that over here I have cubic centimeters on the top. I better put cubic centimeters on the bottom. So let's go ahead and write 1 cubic centimeter on the bottom, and then that means that 19.3 grams needs to go up on top. At this point, I can double check that everything cancels. Cubic centimeters cancel out quite nicely. Grams cancel out quite nicely. Everything cancels, which means I know I've set this problem up correctly. The only step left is to multiply 7.2 times 19.3. Plug that into my calculator. 7.2 times 7.2 times 19.3 divided by 1, and this comes out to 138.96. All right, so that's the answer that's spit out by my calculator. Now, what about sig figs though, right? So let's look at our sig figs real quick. Notice that we started with, we have 1, 2 here, we have 1, 2, 3 here. So my quote-unquote worst number only has 2 sig figs. So I can only keep my first 2 sig figs like that. So I actually need to rewrite this number. And I need to write it as a 1. And then do I round up to 4 or do I round down to 3? I'm going to round up to 4 because of this 8 right here. Okay. Now it's also important to note that I can't just leave it as 14, right? If this was your bank account and someone said, how much money do you have? You wouldn't say, I have approximately $14. You'd say, oh, I have approximately $140. Now, as long as I don't put a decimal point in there, this is not a significant zero. So I can go ahead and write that as 140. Now, the next thing is, what about my units? Well, my question mark was grams, right? So 140 grams, and this is how I should report my answer. So don't let me trick you. You know, if I ask you what's the mass, you don't want to say this, okay? You want to report it as this because this shows your understanding of significant figures. Now the final thing that I just want to mention briefly, you won't be using this a lot in this course at all, but if you plan on going into a health profession, you know, nursing or so forth, you might come across something known as specific gravity. So specific gravity is a quantity that compares the density of a substance with the density of water at the same temperature, which seems like a lot of words for something very simple. All it is you're taking the density of your substance itself and then dividing it by the density of water. Now the interesting thing is that the density of water is 1.0 grams per milliliter, right? And so really you're just dividing by 1. So if I tell you that a substance has a density of 19.3 grams per milliliter and I ask you for the specific gravity of it, all you'd say is, well, grams per milliliter cancels grams per milliliter, so if the density is 19.3 grams per milliliter, the specific gravity is 19.3. And there are no units again because they canceled out over here. Okay, so again, not commonly used in chemistry at all. Doesn't seem terribly important, but what can it be used for? Well, this can be used for, let's say that a patient is suspected of having diabetes, right? So you want to measure the specific gravity of their urine to see if they're passing a bunch of glucose in their urine. So specific gravity, you can use a little instrument that measures specific gravity, and you can actually figure out what it is and figure out if it's higher than normal. You know, there are also tests that you can test specifically for the glucose, probably more useful, but just so you're aware of what specific gravity is. And I know this has been a long section, but thanks for sticking with me and learning all about measurements. We will be using this throughout the entire course, so you know, if you need to go back and review some of those slides about you know, the domino method, feel free to. Also, you know, we're going to be using this again, so I'll be reviewing this as we move along throughout the course.